Hello, good evening. This is Professor Khan, and in this video I am trying to go over pump sizing calculation and make sure that you know how to fill that calculation sheet correctly. So given this problem, probably you will have a house plan. I have this house plan. It's not something that you have already, and I did calculate the heat loss for this section of the house, 4,000, 3,000, 6,000, and 2,000 for this section. And I've decided that I'm going to have two loops into the house using two zones. So this is going to be my loop 1, my loop 2, and this is going to be my location of the boiler. And it is one-story house, and I'm going to put all the equipment in the basement, and you go up to a series loop. I'm just assuming it's going to be a series loop at this state, and keep it at that for now. Okay, so let's check that out. How do we do that? So this is my loop, this is the heat, this is where the pump is gonna go and push the water all around this loop. So the first thing we said that we need to know about the pump is the GPM. Then we need to know the head. So whenever you go to the warehouse or the hardware store and you want to purchase a pump, they ask you for the head and the GPM. So the GPM, we said, if you look at this pump calculation sheet, probably you see the first equation over here. I'll try to get it a little bit closer, and it's GPM equal heat load over 500 over delta T. So GPM will equal total heat load over 500 times delta T. Okay, let's do this calculation for here. And I'm going to keep this on the side so you can look at it and see what I'm talking about while I'm doing the calculation. And I'll have my calculator so you can see what am I doing. So the total heat load is the entire heat load for the loop. So in this case, it's going to be, I will write it down as well. It will be total. No, it's not very clear. I'll use something else. So total heat will equal 4,000 plus 3,000 plus 6,000 plus 2,000. Okay, so calculating, adding all these together using the calculator again. 400,000 plus, do not add extra zeros, I tend to do that. And we get 1,500, so that's actually 15,000, so that's 15,000 BTU. Okay, that's the total. So now we just plug this into the equation over here and over here, and so GPM will equal 1,500 over 500 times delta T, which is usually 20, so 20 degrees, and so 1,500 over 500 over 20, 1.5 GPM. If you get some crazy number, probably you did divide, then multiplied, which is not correct. So we got the GPM, and that's the first number we need to have for this loop. And again, this is very small circulation and small loop. So we get the first part, which is the GPM. Going forward, we need to do what's called the equivalent length method, and this is a breakdown of these calculations. So the major equation that we are going to use, I'm going to take a new page now, so we know it's 1.5. I'll put that in the page over here. It's going to be 1.5, and to expand this a little bit to make it look nicer, 1,500 over 500, and the 500 actually is a conversion between gallons and feet cubed and the temperature. So here we need to use this equation to find something called the equivalent length. So pump head is the pressure loss, and this pressure is calculated in feet. So what you need to do is first try to find the elements of this little equations over here. I will try to, okay, let me get it closer. It's over here, it's in the sheet. And again, these calculations are really not that difficult if you know how to get those numbers to fill in the blanks. Times A times GPM to the power of B. Okay, so first thing you do is we got the GPM, we calculated that. B is a lookup from the book based on the pipe size. In this case, it's going to be 1.75 because that's from the book. And which page? I'll try to show you which page. Again, we are in chapter 6. And if you go to page, again, we're using copper for hot water. So here is the table. It's page 101 in my book. And B is going to be 1.75. And if you look here, it's based on the size of the tube. So we're using 3/4, or you can use whatever you want based on it could be anything up to 2 inches, but the most common is 3/4. And we can go and verify that. You saw that the last lecture. And A is based on the temperature. If I'm going to be using type A or type B, it's better to stick with 180. So in this case, we have 0.274. So I'm going to put that here as 0.274. Okay, we got that, we got the numbers. What we need now is the equivalent length. What is equivalent length? It's over here. LE is length of the total pipe you're going to use in your loop, like all the pipe you're going to lay out. And you see this in yellow. I did lay out some pipe. Total length of tube plus the conversion of losses in elbows into length, and that's why it's called the equivalent length. And where do you find that? So if you go into the same opposite page from 101 is 100. Page 100, it's a copper fitting equivalent length over here, and you'll see that a conversion for most elbows into regular feet length. So if I look at this page, if I imagine I'm doing your project, so this is going to be the length of the tubes going all around. What is the length of this pipe? You can eyeball it to become something around 10. I did some kind of random calculation here somewhere. I don't know if I have it. No, this is the total heat loss over here, 1500. So I'm going to add these lengths together. So let's do it randomly to see what is the equivalent length. And I'm going to start by this leg. And first of all, we're going up by 8 feet because the boiler is in the basement. So I'm going to go with 8 plus all the way here 10 plus, and I'm going to go with the length of the room, right? 10.3. I'm going to add another 10.3. That's 20.6. You see where this is 10.3 and 10.3 over here. So I'm going to put that as 20.6, which is 20.5, right? Because 6 is 6 inches. And if I go from here to here, all the way, again, there's going to be some additional length I will talk to you about soon. So 10, this is, what is the length here? 13 and 13, that's 26 feet. Plus going from here to here is going to be the same as here, right? So I can do that again, 20.5 feet. And going from here to here is going to be, I'll say it's another 10 feet. It's better to err on the side of excess than less than that. And if you think about the pipe is going from going up and sideways. So it's good to give every radiator 2 feet on each side, 1 foot on each side to connect for connections, assuming that they're not going to go straight, just in case. So we'll say 1, 2, 3, 4, 5 radiators times 10 times, so 5 radiators times 2 feet, that's another 10 feet, and that is for radiator raise. Okay, so we got that for total length, and that's going to be the length of the pipe. Length of pipe. Okay, I'm going to multiply, I add this together, 10. Again, it's good to double check your calculation, do it twice. 0.5 plus 10 plus 10. I get 105, which is what I got actually before. So 105 feet. Okay, so that's the length. What about the elbows? Okay, so now I'm gonna need some elbows, and I'm going to assume in this case, for the sake of simplicity, that we only going to use 90 degrees elbows. So if I'm going to imagine this drawing over here, I'm going down from the boiler, up from the boiler, then an elbow, then going up to the radiator, coming down, and so on. These are my radiators, right? So this is 1, 2, 3, 4, 5. Okay, so I'm gonna have 4 elbows for each radiator, and at least 2 elbows coming all the way from the boiler. This is my boiler here. So I will count the radiators. I'm gonna have 1, 2, 3, 4, 5. I forgot to highlight this one. 5 radiators times 4 times 4 elbows. That is 20 elbow, which is 90 degrees. And we'll add 2 more for the radiator, so let's say 22 elbows. Converting that into feet, so that will go into this sheet over here. So LE is the total length, which was 105, and we have how many elbows here? 22. And each, if I look at the table here, you'll see that each elbow around 3/4 and 90 degrees is 2 feet. So that's 2 feet, and I'm not going to use any of these. It's going to be 105 plus 44. But that's multiplication of 2 times 2, 22. And in here, I'm going to do this so I don't mess it up. 105 plus 42. I got 174. Okay, so now I got all the numbers I need to fill into this equation. So I have in this number LE, which is 147. A is 0.274 and 1.75 for B. And what is the GPM? 1.5. And I will do the just chug and plug in the calculator. So one thing I need you to think about is raising is this little thing in here that's kind of annoying. How you gonna raise to the power of B? I'll show you how. If you look at your calculator, there's always a button here that says to the power of. I don't know if you can see it. It's X to the blank, and it looks like a little hat. Looks like this symbol over here. So if I do 1.5 to the power of 1.75, see the symbol? You might find this symbol in your calculator and should do the trick. And I got 2.3, and this will remain the same as 0.27, and 147 over 100 is 147 over 100 is 1.47. Okay, I'll multiply those three together. 1.47 times 0.27 times 2.03, and I got 0.8. Now you probably think that 0.8 feet of pressure, that's not a lot, but again, this is a very simple loop. It's only one story. That's what we are going to have to counter for pressure, just pumping around one loop. So you can decide, am I going to have 2 pumps or 1 pump? That's for you to decide. So total head pump is going to be this number plus the static, which is the height. So if I look at again my picture here, this is the height from the boiler to the first floor, and I will say it's 8 feet as an average ceiling. So it's going to be 8 feet over here plus this number, which is 0.8. So it's going to be 8.8 feet, and that's going to be the pump head that we need. If we get a pump that's only 8 feet, it's not going to be able to push the fluid around. And again, that was a very, very conservative way to do the calculation. So hopefully this makes sense, and please shoot me any questions that you might have. Thank you.